And welcome back to Math 143, Finite Mathematics. Today we begin Chapter 6, Sets and Counting. Before we study probability and counting techniques, we first need to understand sets. Okay, sets are one of the most fundamental ideas in mathematics. In fact, almost every branch of mathematics uses sets in one way or another. Today, we will learn what is a set, how to describe sets, and how to perform operations such as unions, intersections, and complements. By the end of today's lecture, you should be able to define a set and its elements, use set notations correctly, and write sets using roster notation and set builder notation, determine whether two sets are equal or not, identify the subsets, describe the empty set and universal set, perform union, intersection, and complement operations. Finally, interpret the Venn diagrams. Okay, let's begin with the basic definition. What is a set? So, a set is a well-defined collection of objects. Collection of objects. The objects inside the sets are called elements or members of the set. The objects inside the set are called elements or members. Usually, sets are represented using capital letters such as A, B, C, uppercase letters. Also, elements are represented using lowercase letters like lowercase letter A, B, C, anything. Okay. Usually, sets are represented using capital letters such as A, B, C, and so on. Elements are represented using lowercase letters A, B, C, so on. Okay, let's see the simple example for a set. For example, set A, we have numbers 1, 2, 3, 4, 5. So, set A, we have the numbers 1, 2, 3, 4, 5. Within braces, we will discuss more about the set notations. So, almost just we need to discuss the example right now, but we will discuss more about the set notation. So, here you can see that the set A, which represent by the uppercase letter A, and then the elements are 1, 2, 3, 4, 5 within braces. So we must represent the set within braces. Here the numbers 1, 2, 3, 4 and 5 are the element of the set. So those numbers here, the numbers 1, 2, 3, 4 and 5 are the elements of the set. Okay, then let's go for the notation. the membership notation first. So we use two important symbols during the chapter 6. So let's call membership notation. So if an element belongs to a set, if an element belongs to a set, we write A belongs to set A. The usual notation, this means belongs. So this means A belongs to set A. If an element does not belong, we write A does not belong the set A. So this means A does not belongs to set A. Right? So let's see the counter example. Let's use the same example as we used. Example, set A, we have 5 numbers, 1, 2, 3, 4, 5. Okay, is number 1 an element of A? Is number 1 an element of set A? Right? Yes. Yes. So we can write 1 belongs to A. 1 belongs to set A. Okay, then is number 6 an element of set A? The answer should be no, because the elements of set A elements are 1, 2, 3, 4, 5. No, number 6 is in the set A. So the answer should be no. We write 6 does not belong to set A. 6 does not belong to set A. Okay, let's see the one more example. Example, let set B the vowels A, E, I, O, U. Is E in set B? Is E in set B? Yes. E belongs to B. Is X in set B? No, X does not belongs to set B. Okay, as I mentioned earlier, now we wanted to know how to describe a set, how to perform a set. So there are 2 common ways to describe a set. The first one is called the roster notation and the second one is called the set builder notation. Okay, let's go for the ways to describe a set. So there are two common ways. The first one is roster notation, and the second one is set builder notation. Okay, let's begin with the roster notation. Roster notation simply lists every element inside the braces. So the roster notation simply lists every element inside braces. For an example, the even numbers less than 10. The even numbers less than 10 are within braces. Let's say the set A, the even numbers less than 10. The set 2, 4, 6, 8. Just list the every element inside the braces. The prime numbers less than 20. Let's say set B, prime numbers less than 20, the numbers that has the common factors 1 and itself, 2, 3, 5, 7, 11, 13, 17 and 19. So roster notation works well whenever we can list every element, right? The roster notation works well whenever we can list every element. Okay, then let's go for the set builder notation, the second method. Sometimes listing every element is impossible. Instead, we describe the rule. For an example, x is an even integer between 0 and 10. So, read it loud. X is even integer between 0 and 10. The set of all x such that x is an even integer between 0 and 10. So, it means the such that. What does it mean? Let's say we can use the example. Let's use the example. Example, the set of all x such that x is an even integer between 0 and 10. The set of all x such that x is an even integer between 0 and 10. So it's usually describe the rule. So here we describe a rule. So we can write it as x and the small vertical bar which represent this word such that x is an even integer between 0 and 10. 0 and 10. The vertical bar explains the word such that. So the set builder notation is for sometimes the list in every element is impossible. Instead, we describe the rule. Okay. Hope you understand the difference between two notations, the roster notation simply list every element inside braces, and the set builder notation we describe a rule because sometimes the list in every element is impossible. Right? Okay. So highlighted this area because you can easily find out the two different notations. Okay, then let's see example for the roster notation. Let's say extra example. Write positive integers. Okay, write positive integers. So can we list all positive integers? Can we list all positive integers? Is it possible? No. So we can write describe in the set. The answer should be no. Therefore, so we write x is a number such that x is a positive integer, right? X is a positive integer. X is a positive integer. Okay, I will give you the practice examples. Please pause the video and try it by yourself. Practice. Write each set in roster notation. Days of the week, single digit non-negative integers, multiples of 3 less than 20. Days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Roster notation within braces. Single digit non-negative integers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Multiples of 3 less than 20. 0, 3, 6, 9, 12, 15, 18. Okay, take your time and then convert one of them into set builder notation. Convert one of them into set builder notation. Okay, then let's move forward. How we can say that two sets are equal? So equality of sets. So the two sets are equal if they contain exactly the same elements. Two sets are equal if they contain exactly the same elements. The order does not matter. The main idea or main note, the order does not matter. Repetition does not matter. Let's see the example. Set A, 1, 2, 3. Set B, 3, 2, 1. Are these equal? Yes, because they contain exactly the same elements. Yes, because they contain exactly the same elements. Okay, then now compare the set A 1, 2, 3 and set B 1, 2, 4. So these are not equal because set A contains 1, set B 1, set A 2, set B 2, but number 3, number 4. The elements are not equal. These two sets A and B are not equal. Okay, then let's move towards the subsets. Subsets. A subset is a set whose elements are all contained in another set. A subset is a set whose elements are all contained in another set. So we write the symbol, the subset, this, right? So let's say A is a subset of B. A is a subset of B. Symbolically, we write it as A is a subset of B. So this means subset. Example, let's say set A 2, 4, 6. Set B 2, 4, 6, 8 and 10. So let's see, every element of set A belongs to B, right? Every element of A belongs to B. Therefore, set A is a subset of B. Set A is a subset of B. Extra example, is the set 1, 3, 5 a subset of the set this? Yes, because every element in set 1, 3, 5 contains in the second one. Next is 2, 6 is 2, 6 a subset of 1, 2, 3, 4. No, because 6 does not belongs to the larger set. No, because 6 is not in the larger set. Okay, then how to write in symbolical way? We write, let's say, is not a subset. Not a subset, like this. So let's say A is 2, 6, B 1, 2, 3, 4, A is not a subset of B. Not a subset of B. Okay, now we wanted to know the two special sets. Two special sets. The first one is empty set. Empty set. The empty set contains no elements. The word empty sets, empty, there are no elements. So, the empty set contains no elements. Symbol, we use this or no elements. Let's see the example. Natural numbers. Less than 0. So, there are none because the natural numbers are counting numbers such as 1, 2, 3, 4, 5, 6 and 4 upward. Therefore, there are none of the natural numbers below 0. Then, therefore, the set is empty. And the second one, the second special set which we wanted to know during the chapter, the universal set. Universal set. The universal set contains all elements under consideration. The universal set contains all elements under consideration. For an example, before that, the symbol we use the universal set, uppercase letter U. Example, the numbers from 1 through 10. Numbers from 1 through 10. Then the universal set which contains all elements under consideration, everything else U 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So let's say next, Venn diagrams. Let's modify these as not the numbers, let's say integers, right? If we say numbers, then it can be 1.5, 1.2, everything, but we can't write it all here, therefore integers from 1 through 10, right? Okay, now move forward, Venn diagrams. Again, before moving to the Venn diagrams, the empty set that contains no elements, universal set contains all elements under consideration, a subset A subset is a set whose elements are all contained in another set. Okay, then move forward. The Venn diagram. The Venn diagrams help us visualize the sets. Venn diagram helps us visualize sets, right? So let's draw the Venn diagram. Okay, here the rectangle represents the universal set. Rectangle represents the universal set. Inside the rectangle, we can represent the sets drawing the circles. Sometimes we have like this, right? These circles represent sets. Let's say set A, set B, set C, or any. So, Venn diagrams make us the set operations much easier to understand. The universal set represented by the large rectangle. Inside that rectangle, we can draw the subsets. Okay, the main idea, Venn diagrams make set operations much easier to understand. Okay, then let's move forward to the set operations. The first one we call the union. The union combines everything. Write in symbolically A union B. A union B. A union B. The definition: all elements that belong to A or B or both. A union B, all elements that belong to set A or B or both. Let's draw the Venn diagram. Here we have the rectangle space which represents the universal set, and let's A and B are two sets, right? So you can see that set A and set B. The all elements that belongs to A or B or both, the space which covers the entire circle area, and A union B, which combines everything in both A and B, A or B or both. Let's get the example. Example, set A 1, 2, 3, 4. Set B 3, 4, 5, 6. What belongs in the union? That means A union B, the elements in A or B or both. So 1, 2, 3, 4, 5, 6. Notice 3 and 4 appears only once. So in set A, we can see that 3 and 4, set B 3 and 4, but within the union set, we don't need to put that repetition. 1, 2, 3, 4, 5, 6. Just appear only once. Okay. Before draw into the Venn diagram, move towards the intersection afterward. Let's draw the Venn diagram for the count example. Okay, the second set operation, intersection. The intersection contains only the elements common to both sets. The intersection contains only the elements common to both sets. So we can extend this beyond to the two sets, but in this chapter, most of the time we use two sets. That's why I explained this intersection for the two sets. If not, we can go for the more than two sets. So let's write, let A and B are sets, two sets. Then write the intersection A intersection B. A intersection B. Within the rectangle space, which represent the universal set, inside the universal set, we have two sets, A and B. Only elements common in both sets. So which area? The intersection represent the area, the common for both set A and B. A intersection B. A intersection B. Let's get the example. The same example as we discussed in here. Let's go. Right here. Okay, set A and set B. Then, therefore, A intersection B, common elements. What are the common elements? 3, 3, 4, 4. Then it should be 3, 4. 3, 4. If two sets have nothing in common, their intersection is empty. If two sets have nothing in common, their intersection is empty. Such sets are called disjoint sets. Important. Such sets are called disjoint. disjoint sets. If the two sets have nothing in common, then they are disjoint. Okay, then let's draw the Venn diagram to represent both set A and B. Let's draw the Venn diagram in here. Okay, the universal set and two sets A and B. Let's say A, B. So A intersection B, we found that 3 and 4. Therefore, number 3 and 4 must be in the common area. The common area. Then set A contains 1, 2, 3, 4. Then other elements 1, 2, 3, 4. This entire circle contains the set A. And set B contains 3, 4, 5, 6 here. Right? Okay. I hope you understand the difference between the union and the intersection, the two major set operations. Okay, then let's see how to represent the disjoint set. So we have the universal set. Let's say set A is here, set B is here. They have no common outcomes, therefore disjoint set. Okay, let's go for another example quickly. Let set A 2, 4, 6. Set B 1, 3, 5. Draw the Venn diagram. So universal set, set A 2, 4, 6. A union B 1, 2, 3, 4, 5, 6. A intersection B empty. Therefore, two sets are disjoint. 2, 3, 2, 4, 6, 1, 3, 5. Set B. Right? So A intersection B is empty. Next, move forward. Now we know the union of the set, intersection of the set, the complement. Let's go for the third one, complement. The complement contains everything not in the set. The complement contains everything not in the set. We write the symbol A complement, A prime or A complement like this. Okay, let's see the example. The universal set contains the numbers 1, 2, 3, 4, 5, 6, 7 and the set A which contains 1, 2, 3, 4. Then what numbers are not in set A? What numbers are not in set A? So the numbers 5, 6 and 7. Therefore, the A complement is 5, 6, 7. The Venn diagram, we can draw it as the Venn diagram here. Set A 1, 2, 3, 4 and the universal set here. All the entries not in set A, outside the circle. 5, 6, 7. Right? Okay. One more quick example. Display the Venn diagram from the notes and write down the notation. Okay. Let's go for the Venn diagram. There are, let A and B are two sets. Quickly summarize the Venn diagram thing. We have the universal set which represent the rectangle area. Right? Okay, let's go for the set A first. We have the rectangle area, the universal set. Let's say set A. Universal area, let's say set B. Let's add set B, the second set. Set B, the universal set, right? If two sets A union B, we can draw it as separate sets with the disjoint, or like this, A union B, A union B, right? Also, then A intersection B, that is the area common in both A and B. A complement, so we have drawn the A here, then A complement, the outside A complement. B complement, B here, outside of B complement, right? So let's say we have A union B like this, A, B, then A union B complement means the all outside A union B, right? Also, A intersection B complement, if we have A intersection B here, then all outside here we can see the A intersection B, all outside area, the complement, right? Okay. I will give you the more practice problems. Please make sure to practice those problems. Practice problem number 1. Let A 3, 6, 9, 12 determine whether each set is true or false. Each statement, the first one, 6 belongs to A. Second one, 10 belongs to A. Third one, 12 does not belongs to A. Pause the video and review the answers. Second practice problem. Using roster notation and set builder notation, write the odd numbers less than 15. Okay, take your time. Okay. Practice problem number 3. Let the set B is which are subsets first one 1 3 5, second one 2 6, third one empty. Okay, pause the video. The empty set. The empty set is a subset of every set because the empty set is considered a subset of every set because we can say that the empty set, this one, is a subset of every set. The practice problem number 4. Number 4, let A 1 2 3 4, B 3 4 5 6, find A union B, A intersection B, and A complement. Assuming the universal set is okay. It is easy to draw the Venn diagram to get the answers. The universal set which contains number 1 up to number 7. Set A 1 2 3 4, set B 3 4 5 6. Let's say set A, we can see that 3 and 4 are common in both set A and B. Therefore 3 4, then 1 2 5 6, outside 7. A union B 1 2 3 4 5 6, A intersection B 3 4, A complement 5 6 7. Okay, before we finish, let's review some common mistakes. The first one is confusing the symbols. The symbol is used for elements, and this is used for sets, subsets. Thinking that order of element matters, it does not, right? So the order of elements does not matter. The common mistake thinking that the order of elements matter. It does not. And repeated elements in the union. So each element appears only once. Also, forgetting that complements are taken with respect to the universal set. Confusing union and intersection. Union means everything in either set. Intersection means only what they share. The union means everything in either set. Intersection means only what they share. I hope everything clear so far. Let's summarize today's lesson. Today we introduced the language of set theory. We learned what sets and elements are, how to use set notation, how to describe sets using roster notation and set builder notation, how to identify equal sets and subsets, and how to work with special sets such as empty set and universal set. Finally, we studied three fundamental set operations: union, which combines elements from both sets; intersection, which contains only common elements; complement, which contains everything not in the set. These concepts provides the foundation for the counting principles and probability topics that we will study in the next chapter. Thank you for watching, and I'll see you in the next lecture.